When you think about building a physical house, the plumbing is usually pretty straightforward. You have like one main water line coming in from the street, and pipes just branch out linearly to the kitchen, the bathrooms, the laundry room.
Right. Yeah, it makes sense. It's a highly visible, uh, predictable flow of resources.
Hmm.
The exact point of origin, the path it travels,
Hmm.
and, the termination point. It's centralized and simple.
Exactly.
Um,
But imagine if suddenly the kitchen sink just wasn't allowed to connect to that main water line anymore. Like, imagine if you had to run a completely separate, dedicated subterranean pipe all the way from the street just for the dishwasher.
oh, man.
And then another completely isolated pipe just for the upstairs shower. And the golden rule is that none of these pipes are ever allowed to touch or cross paths. Suddenly, your straightforward plumbing looks like this chaotic, invisible labyrinth buried under the foundation.
That is actually the perfect visual for the absolute headache of modern cloud network architecture.
Right.
I mean, you start out thinking you're just connecting a few simple pipes, and you end up building an incredibly dense routing labyrinth.
Right.
And when something breaks or, a packet drops,
Hmm.
you're just scaring into diagnostic muddy waters.
And that chaotic, invisible plumbing is exactly what modern cloud network architecture looks like if you aren't careful. So today, for this deep dive, we're cutting through the jargon to look at the three heavy hitters you really have to master to avoid building that labyrinth, which are VPC Peering, Transit Gateway, and PrivateLink. Because, knowing what these tools do in isolation is easy. It's knowing the catastrophic traps they hide when you combine them that's the real challenge. So by the end of this deep dive, you are going to understand exactly how to navigate these complex multi-VPC architectures. Okay, let's unpack this. We have to start with the most foundational connection. Two VPCs need to talk. The immediate instinct is to use VPC peering. I mean, it's just a direct string and tin can telephone between two networks, right?
Essentially, yes. It is a direct one-to-one networking connection. It allows you to route traffic between two VPCs privately using private IP addresses, so devices in either VPC communicate as if they're sitting on the exact same physical switch.
Okay, I like simple. My house has a tin can, your house has a tin can, we pull the string tight and we communicate privately. But there's this massive flashing red warning light in our sources that architects always seem to ignore, and it's this rule: transitive peering doesn't work.
Ah, yes. The classic trap.
And I really have to push back on this right out of the gate. If network A is peered with network B, and network B is peered with network C, why on earth can't A talk to C? I mean, is this just some, artificial limitation cloud providers invented to force us to buy more expensive routing tools? Because it honestly feels like a software constraint designed to sell a solution.
What's fascinating here is that it's so tempting to look at it as a monetization conspiracy. But disabling transitive pairing is actually a highly intentional, really critical security and stability choice.
Wait, really? It's intentional?
Oh, absolutely.
Well,
Let's look at the mechanics of why. First, think about the blast radius of a security breach. If you manage network B, you might trust network A enough to peer with them,
okay.
and you might trust network C enough to peer with them. But that does not mean you want to be legally or technically responsible for letting network A access network C's data through your infrastructure. You would become this unregulated middleman.
Oh, okay. So it's about implied trust. Just because I give my house key to my neighbor and I give my house key to the plumber doesn't mean I want the neighbor and the plumber hanging out in my living room together while I'm not there.
That is an excellent way to frame it, yeah.
Uh-huh.
But there's a second, much more technical reason, and it involves routing loops and BGP,
Oh, yeah.
the Border Gateway Protocol,
Yeah.
in massive, complex networks. If transit were allowed by default, it would be incredibly easy to accidentally configure a loop. Like a packet of data gets passed from A to B, B to C, C to D, and then D passes it right back to A. Exactly. The packet just spins in circles forever, consuming bandwidth till the entire network practically crashes. So by forcing every single connection to be a deliberate one-to-one peer, cloud providers force architects to be absolutely intentional about every single path. You cannot accidentally create a loop if the bridge is literally physically broken.
Okay, I see the logic there. You contain the blast radius and you prevent these infinite routing loops. But let's follow that restriction to its logical conclusion.
Okay.
If transitive peering doesn't work, doesn't a growing enterprise network just turn into a complete nightmare? I mean, if I have 100 VPCs that all need to talk to each other and they can't transit through a central middleman, the math on that gets ridiculous fast.
You've hit the exact breaking point of VPC peering right there. To connect a network in what we call a full mesh, where every single node connects directly to every other node, The formula is n times n minus 1 divided by 2.
Okay, so for 100 VPCs.
For just 100 VPCs, which are practically nothing for a medium enterprise, you need 4,950 separate individual peering connections.
Wait, almost 5,000 individual string and tin can connections?
Yep.
If one string breaks or like a single routing table gets a typo, you're hunting for a needle in a massive haystack of tin cans. How do you even audit that for compliance?
You don't. It's practically impossible to manage securely at that scale. You can never confidently hand an auditor a report proving exactly who has access to what, because there are 5,000 individual doors you have to manually check.
Wow.
And this administrative breaking point is exactly where the architecture has to completely shift from peer-to-peer to hub and spoke. Enter the transit gateway.
Ah, okay. This is the Grand Central Station concept from our sources. Instead of building 5,000 separate train tracks directly connecting every single town in the state, you just build one track from each town into Grand Central.
Precisely.
The transit gateway sits in the center and handles all the complex routing logic. So Network A sends traffic to the gateway, and the gateway knows which spoke leads to Network C.
That is the mechanical reality of it, yeah. Each VPC only needs one single connection, which we call an attachment, to the transit gateway. So you go from managing 4,950 peering connections to managing exactly 100 attachments.
That's a massive difference.
It's huge. You manage your routing tables in one centralized location. It fundamentally solves the scale issue we just talked about.
But wait, if this magical Grand Central Station exists and completely simplifies the architecture, why would anyone ever use VPC peering? If I'm an architect, why wouldn't Transit Gateway be my default answer, like 100% of the time?
Because treating a transit gateway as the default answer is the most expensive trap an architect can fall into.
Oh, really?
Oh, yeah. You're trading administrative overhead for an actual financial and performance penalty. You really have to look at the physics of how the tool operates.
Okay, let me guess. It's latency. By introducing Grand Central Station, you are adding a middleman. The string and tin can is direct, but the gateway requires the data to travel to a central router, get processed, and get pushed back out. For a high-frequency trading platform, that extra hop is probably a deal breaker.
Latency is a factor, absolutely. But the truly catastrophic trap is the cost model.
A cost model.
Yeah, VPC peering is generally cheap. You're mostly just paying standard data transfer rates. Transit Gateway, however, changes the financial equation entirely. You pay an hourly fee just to keep each attachment open, but more importantly, you pay a per gigabyte data processing fee for every single byte of data that flows through that gateway.
Ah, a toll booth.
A very aggressive toll booth. I've seen disaster scenarios where a data engineering team needed to migrate, like 50 terabytes of analytics data between two internal VPCs every single night.
Oh, boy.
Yeah. They used a transit gateway because it was already set up and quote-unquote simpler to just point the traffic at the hub. They didn't realize they were paying a processing fee on 50 terabytes a day. They essentially bankrupted their department's monthly cloud budget in 4 days, all for traffic that never even left their own infrastructure.
Ouch. Okay, so precision tools are still mandatory. If I have a heavy-duty data lake constantly talking to a machine learning cluster, I bypass Grand Central completely and run a direct VPC peering connection just between those two to avoid the toll booth.
Exactly.
But for the 100 little department networks that occasionally need to read the corporate intranet, I use the transit gateway.
Precisely. You balance the administrative nightmare of full mesh peering against the financial penalty of transit gateway data processing.
Okay, that makes perfect sense. So Transit Gateway connects entire networks broadly, and peering connects entire networks directly. But what if you don't want to expose an entire network at all? Let's say you have a highly secure environment, and you only want to share one specific API. You don't want broad access.
This brings us to PrivateLink, right?
It does, and this raises an important question about security and access. We're moving from connecting whole networks to exposing specific services. PrivateLink allows you to expose a specific private service without exposing the entire network to a transit gateway or a peering connection.
Here's where it gets really interesting. The visual I use for PrivateLink is a highly secure, bulletproof VIP drive-through window.
I like that.
Yeah, if your VPC is an exclusive private restaurant, connecting a transit gateway is like opening the front doors and letting a whole tour bus into your dining room. Even if you have routing rules checking their IDs, those people are physically standing inside your building.
But PrivateLink is the drive-through. You never let anyone inside the network. You just hand them the specific menu item they requested through the window, and they drive away.
The security implications of that drive-through model are massive. By using PrivateLink, the consumer of the service connects to it privately. The traffic never traverses the public internet, and crucially, you never have to manage overlapping IP address spaces.
Oh, that's a good point.
Right. If both networks happen to use the exact same internal IP range, peering and transit gateways will break down. PrivateLink doesn't care, because the networks aren't actually joining.
But the mechanics of building this VIP window get incredibly dense. I mean, you constantly hear about gateway endpoints versus interface endpoints. If you are a listener trying to sketch this out on a whiteboard right now, how do you actually draw the difference between a gateway and an interface?
It is honestly the most common point of confusion for engineers learning this space. So let's break down the physical mechanics. Start with the gateway endpoint. Do not draw a physical window on your whiteboard. Instead, draw a magic signpost in your network's routing table.
Wait, just a signpost, no actual hardware?
Correct. Gateway endpoints only support two specific services, S3 and DynamoDB. When you create one, you aren't deploying an appliance. You are literally just injecting a rule into your router that says, if any app in this network tries to reach S3, do not send that request out to the public internet. Divert it down this invisible free tunnel on the cloud provider's backbone.
Oh, wow.
Yeah, it costs nothing, but it's strictly limited to storage and databases, and it only exists as a line of text in a routing table.
So it's just a free set of directions. That's great. But if it only works for two services, what is the interface endpoint? Is that the actual VIP drive-through window?
Yes. An interface endpoint is the physical manifestation of PrivateLink. When you create one, you are actually dropping a virtual network card, an elastic network interface, or ENI, directly into your subnet. It consumes a real private IP address from your network's allocation. It is a physical targetable destination.
But wait, how does an application actually know to use that network card? Like, if I write a script that calls a third-party sauce API, my script is hard-coded to look for a public web address. It wants to go to the internet.
Yeah.
How does the ENI intercept that?
That is the genius of how PrivateLink operates under the hood. It uses DNS hijacking.
DNS hijacking.
Yes. When you deploy that interface endpoint, it creates a private hosted zone in your DNS resolver. So when your application asks, hey, what is the IP address for this external API? Your internal DNS jumps in and says, oh, I know that one. The IP address is actually 10.0.0.5.
Which is the local IP.
Exactly. It's the local private IP of the ENI sitting right next to it in the subnet.
That is wild. It literally lies to the application.
It does.
The app thinks it's talking to the public internet, but the DNS tricked it into talking to the local network card, which then tunnels the data securely to the provider.
Exactly. The application requires zero code changes. The traffic hits the ENI, and PrivateLink acts as a one-way secure tunnel across the provider's physical hardware directly to the service. But unlike the gateway endpoint, because you are deploying physical virtual infrastructure, interface endpoints carry an hourly cost and a data processing fee.
Okay, so we have the full toolkit mapped out. We have the cheap, direct string and tin can of VPC Peering. We have the expensive, centralized Grand Central Station of Transit Gateway. And we have the hypersecure VIP drive-through window of PrivateLink and interface endpoints. The true test of an architect isn't just defining these, it's knowing exactly when to apply them in complex scenarios.
Absolutely. Architecture is entirely about scenario-based problem solving. It's about recognizing the constraints of the real world, cost, scale, security, and applying the right tool to the specific friction point.
All right, let's put this to the test. So what does this all mean? I'm going to look at some massive, complex network architecture scenarios, and you tell me if I fall into the trap. Scenario 1, a massive corporate merger. Company A has 50 VPCs. Company B has 40 VPCs. They need every single employee to be able to access a shared human resources platform, an internal wiki, and the Active Directory servers.
Okay, what's your play?
Broad access, lots of networks, needing a central hub to manage the chaos. I am absolutely not managing 4,000 peering connections. And PrivateLink is too specific if they need broad network-level access to multiple servers. So this is a textbook transit gateway scenario.
Spot on. Broad network-to-network connectivity at scale absolutely demands a central hub. Okay, scenario 2. You have a specialized proprietary machine learning algorithm in your VPC. You want to sell access to this algorithm to 500 different enterprise customers, but you absolutely cannot let those customers see anything else in your network, and their networks cannot overlap or talk to each other.
Okay, that's the VIP drive-through window. They're buying the burger, but they can't come into the kitchen. I project an interface endpoint into each customer's network using PrivateLink. They hit the local IP, get the algorithm, and stay completely isolated.
Perfect application of PrivateLink. Now, scenario 3. Let's see how you handle a hybrid.
Oh boy. Okay.
You are a massive sauce provider. You have an incredible internal analytics API
Right.
that you need to expose to 500 different enterprise customers. So far, this sounds like PrivateLink, right?
Great. Expose an interface endpoint. Easy.
But here is the catch. Your 500 enterprise customers are massive corporations, and they don't just have one VPC. Each of your customers has their own internal network of 50 VPCs managed by their own transit gateways. They want every single one of their internal VPCs to be able to hit your API.
Oh, wow.
How do you design this? Do you peer with their transit gateways?
Oh man, if I peer my network with their transit gateways, I'm opening up a routing nightmare, and I'm probably exposing my SaaS backend to their entire corporate network.
Right.
But if I use PrivateLink, do I really have to drop an interface endpoint into all 50 of their individual VPCs? That would mean managing tens of thousands of endpoints across all my customers. That's a billing and administrative disaster. I feel like neither tool works here.
This is the ultimate architectural trap, and the solution requires combining the tools.
Really? How?
You, the SaaS provider, use PrivateLink to drop exactly one interface endpoint into a single dedicated shared services VPC within the customer's environment.
Okay, so one VIP window exists in their environment.
Yes. Then the customer attaches that specific shared services VPC to their own internal transit gateway. So when any of their 50 internal networks want to reach your API, their transit gateway routes the traffic to the shared services VPC, hits the single interface endpoint, and the data tunnels securely back to you.
That is brilliant. You used the transit gateway to solve the scale problem on their side of the wall, but you use PrivateLink to maintain absolute isolation and security on your side of the wall.
Exactly. You combine the scale of hub and spoke with the granular security of the interface. If we connect this to the bigger picture, avoiding architectural traps requires deeply understanding those three core lenses. The exact scale of your need, which dictates transit gateway, the need for granular isolation, which dictates PrivateLink, and the limits and costs of basic connections, which is understanding when direct VPC peering is actually the smartest financial play.
Scale, isolation, and cost. If you look through those three lenses every single time you draw a line between two boxes on an architecture diagram, you won't accidentally build a labyrinth.
Absolutely. But, before we wrap up this deep dive, I want to leave you with one final lingering thought about the broader implications of all these tools.
Okay, what's that?
Modern enterprises are increasingly relying on transit gateways and private links to pull every single internal tool, database, and microservice completely off the public internet. The goal is absolute security. But are we unintentionally creating an entirely invisible dark web of corporate infrastructure?
Wait, what do you mean by a corporate dark web?
Think about it. If everything becomes a perfectly isolated, privately linked endpoint, shielded by DNS hijacking and completely invisible to traditional public routing, how will the network architects of the future even begin to map these environments?
Oh, well.
We are building massive, invisible digital cities in the dark. If the map only exists in thousands of fragmented routing tables and private hosted zones, troubleshooting a systemic failure in 10 years is going to require an entirely new kind of digital archaeology.
That is a terrifying and honestly fascinating thought. We are building the ultimate secure fortress, but we might be throwing away the blueprints in the process. Well, next time you try to ping an API, think about the invisible labyrinth of peering connections, gateways, and hijacked DNS requests happening right beneath your keyboard. Keep questioning the architecture around you, keep looking for the hidden toll booths, and we will catch you on the next deep dive.